Hello and welcome to the 12th of our NASA Engineering and Safety Center Guidance, Navigation, and Control webcasts. I'm Neil Dennehy, the NASA Technical Fellow for Guidance, Navigation, and Control, and I'll be your moderator for today's webcast. As I have previously mentioned, the idea to have these hour-long webcasts originated with the members of my NESC GNC technical discipline team, who thought they would be a good way to broadly share their individual knowledge with the rest of the NASA GNC community of practice. We are nominally holding these GNC webcasts on the third Wednesday of every other month at this same time, 2 p.m. Eastern. Please note that this webcast is being recorded and will be made available for subsequent viewing on the NESC Academy site. The link to the NESC Academy site can be found on the webcast registration page. I'm now very pleased to introduce today's speaker, Miguel San Martín from the Jet Propulsion Laboratory. Miguel was born in Argentina and grew up in Buenos Aires. He came to the United States to pursue his university studies at Syracuse University. He has a degree in electrical engineering from Syracuse, and he also earned his master's degree from the Massachusetts Institute of Technology in aeronautical engineering with a specialization in guidance, navigation, and control for interplanetary space exploration. Upon graduation from MIT, he was hired by the Jet Propulsion Lab. Early in his career, Miguel participated in the Magellan mission to Venus and the Cassini mission to Saturn. He was later named chief engineer for the GNC system for the Pathfinder mission, which landed Sojourner, the first robotic vehicle to land on Mars. He later assumed the same role for the highly successful missions that landed the robotic vehicles Spirit and Opportunity on Mars in 2004. Most recently, he was the chief engineer for GNC for the Mars Science Laboratory, MSL, which landed successfully the one-ton rover Curiosity on the surface of Mars on August 5, 2012. He was the co-architect of Curiosity's innovative sky crane landing architecture and also served as its deputy chief for entry, descent, and landing. The complete version of Miguel's biography is provided on the webcast registration site for your reference. Miguel's talk today is entitled The Evolution of Guidance, Navigation, and Control in Mars Entry, Descent, and Landing. I've seen Miguel give this talk, previous versions of this talk, at a number of GNC conferences. He's added some more meat in the GNC, specifically in the GNC area. I think we're in for a real intellectual treat this afternoon. At the end of Miguel's talk, I will moderate a 10-minute question and answer period. You will be able to submit questions to Miguel via the webcast site. I'll now briefly walk you through the mechanics of how to do that. If you look at the snapshot of the webcast panel now being shown on the screen, you will see an expanded look at the toolbar at the bottom right. There are two specific control buttons there on that toolbar that I want to draw your attention to. The first is the Ask a Question button, which is the third button from the left on the actual toolbar. At any time during the webcast, you can use this control button to submit questions to Miguel. Please include your email address or simply your name and center location when you are submitting questions. Because of the 10-minute time constraint for the Q&A period, Miguel will most likely only be able to directly answer a few of the questions that he receives from the audience today. However, as long as we have your email address or your name and center location, Miguel has promised to respond to all the questions that he receives. So I encourage you to submit your questions during the course of Miguel's talk if you can, rather than waiting until the very end of his presentation, as I'll be collecting them up and going through them as we go along. So the second feature on the toolbar I want to highlight for you is the volume control button on the far left. If you place your cursor over that speaker icon there, you can access the volume control slider and use that to individually adjust your computer speaker appropriately. And now, with great pleasure, I'd like to turn this webcast over to Miguel. I believe you're going to find this talk both informative and entertaining.
Great. Thank you, Neil, for that introduction. And it's a pleasure for me to be here. And so we're going to start here this presentation. So we have been very lucky in the GNC community with Mars, because it has given us an opportunity in the last 30 years or so of exploring all sorts of different architectures, starting with Viking in the 1970s, a legged lander, successfully landed two stations on Mars in '76. Then after a period of 20 years, came in the Mars Pathfinder. It was an airbag lander, and very different, and we'll explain that later on why. And it was very successful, and it was first successful airbag lander on Mars. That was in the 90s. And the same was MER, followed later on, another airbag lander with landed the Spirit of Opportunities in the year 2000. Along there also we went back to the legged landers approach with Phoenix in 2008. And finally, we ended up with the sky crane approach of MSL, which landed last year in 2012. So hopefully I want to give you some ideas of why we went through all these different architectures in the Mars program. So when one talks about entry, descent, and landing, or EDL, one needs to talk about certain performance metrics of what is the specifications of the system that dictates how that EDL is going to look like. So one is obvious, is the useful landed mass. We go to Mars to do work, and we want to bring scientific instruments. So you can see, for example, on the top chart, how the amount of useful landed mass have changed through the years, starting with Viking and now finishing with Curiosity at almost 900 kilograms of useful mass. Another metric that is very important in designing an entry, descent, and landing system is the size of the landing ellipse. Okay, we want to have, and that is the dispersions of which we land on Mars. We want to have a small area because the scientists are always looking for places that are, interestingly, from a scientific point of view, and in some cases, there's no good, safe place to land. So the smaller our dispersions, the better the chance, the higher the probability of they being able to go and visit a scientifically interesting place on Mars. And finally, there is also the landing site characteristics. So within that area that we land, we need to put some specifications. We call it engineering constraints in terms of slopes and rocks. And obviously, for example, an airbag lander is more robust to slopes and rocks, as you can see in the bottom chart. The legged lander are less, and the sky crane approach it's somewhere in between. So these are the metrics, and this is another metrics that I didn't put here, which is the height of the landing site. It turns out that the atmosphere of Mars is so tenuous, it's only 1% that of Earth, that we can run out of time to slow down the vehicle before touching down. So we actually we like going to landing sites that are low altitude, so give us more time to do that. So that's another metric to characterize different EDL systems. Systems that allow us to have access to higher landing sites, allow us also to access potentially more interesting, scientifically interesting places on Mars. So here you can see a pretty dramatic example of how the size and weight and mass of our rovers have varied in the last 20 years. It started with Sojourner and to the left, and Curiosity to the right. So now we're talking about almost 1-ton rover now on the surface of Mars. And here, if you want to get a better feeling of the actual size of Curiosity, you can compare it now to a small vehicle like a Mini Cooper. So we made a lot of progress, and that required going through and eventually, in the case of Curiosity, having to come up with new ways of landing on Mars. We also have made a lot of improvements on the size of the landing ellipse, and which allowed us, in the case of Curiosity, to place the landing ellipse inside Gale crater. That was a very interesting landing site for the scientists, and it's a crater of 150-kilometer diameter with a mountain in the center, a mount called Mount Sharp, and where the science is. And so that is a very risky place to land. We say that we land between a rock and a hard place with a mountain in the center and the rim of the crater on the side. And in order to be able to do that and access dramatic places of great science like Gale crater, we had to reduce that landing ellipse. And that's another one of the things that distinguishes the Curiosity architecture relative to the previous ones. So let's go a little bit through the anatomy of entry, descent, and landing. This is pretty much all the entry, descent, and landings are made up of the same type of phases, okay? Although they are implemented differently, but the same type of braking phases. So we arrive about 20,000 kilometers an hour when we touch the upper layers of the atmosphere, 125 kilometers over the ground. And then in 7 minutes, or 6 minutes, depending on other landings like Spirit and Opportunity. In those 6 minutes, that velocity and that altitude have to be reduced to 0. Okay, everything is, as you very well know, has to be autonomous because of the timeline. We could not do this joystick in front of the ground, so the spacecraft has to be totally autonomous, take care of itself. During those 7 minutes, which we call the 7 minutes of terror for obvious reasons, the spacecraft had to go through all these different metamorphoses of exchange, of separating pieces of the spacecraft, heat shield, deploying parachutes. So it's also a mechanically intensive process. And in addition to our beloved GNC, that obviously we have a role to play. But that's the combination of all of that is what makes it so challenging. So the first phase is the entry phase, which the vehicle protected by an aerodynamic shell with a heat shield slows down just due to aerodynamic friction, and it brings the velocity to about it lasts about 4 minutes and brings the velocity of the vehicle to about 1,500 kilometers per hour and at 10 kilometers of altitude. During that phase, 99% of the original kinetic energy is lost. However, that 1% left is still have you traveling at higher than the speed of sound. So we need to do something about it, and that something is the parachute, which we deploy, and 21-meter parachute in the case of Curiosity, and that about 10 kilometers plus dispersions, obviously, and that, you know, that's also a great job of reducing our velocity, but unfortunately, because of how tenuous the atmosphere of Mars is, we're still coming very close. Even after we get to terminal descent, we're coming down at 300 kilometers an hour. So there has to be a third braking phase. You know, we call it power descent, and again, this is an area where the architectures have varied the most throughout the years on Mars, and that's the final architecture where the final braking stage, where a combination of firing thrusters and some shock absorbers and legs or wheels or the sky crane. So that's the third phase that requires some level of firing rockets, and that we call power descent. And now I'm going to take you through each one of these phases and tell you the more salient properties of them. So we start with entry, as I mentioned before, and the big star of the entry phase is the aeroshell. Okay, that's the one that has to protect the vehicle and has a heat shield that needs to, because as that kinetic energy is dissipated as heat, it needs to protect the vehicle inside and to be able to release all that energy. So another interesting aspect of this entry phase is that it could be of two types. It could be a ballistic entry or a lifted entry. On the left side, the ballistic entry, the center of mass of the vehicle is trimmed to be in the center of symmetry of the vehicle, in which case there is no angle of attack. The angle of attack is zero, so it's only drag in this vehicle. And it's ballistic because it behaves like throwing a rock. It just curves ballistically due to the drag and the effect of the gravity. And there is no way to control such a vehicle. You have to predict, understand the aerodynamic properties of the vehicle and the atmospheric properties, where it's going to land, and given the initial conditions. Okay. On the right, we have lifted entry, in which case now we do move the CG of the vehicle. We displace it, in this case, up, away from the center of symmetry in a way that now the vehicle trims at an angle of attack. Okay, and now, just like a wing will do in an airplane, it generates a lift vector. Now that lift vector, now we can use that for multiple things. One, we can use that lift vector for guiding the vehicle in a way that we can actually reduce our dispersions, reduce our landing ellipse sizes. So that's what, you know, that's one use of that lift vector. But another one use of that lift vector is, as I mentioned before, being able to land on high altitude at Mars is a beneficial thing, because it improves the probabilities of finding interesting landing sites scientifically that we can actually go visit. So lift allows us to stay higher in the atmosphere while we slow down and have access to those landing sites. So those are the two uses of lift. So I'm going to talk now a little bit about the history of how this entry phase has been implemented throughout all these different architectures. There's a lot of information here. So we're going to start with Viking. So Viking was a lifting body, like the one that I show you to the right, but it flew lift up. Okay, it did not do entry guidance. It was all about the big concern was being the first lander. There are dispersions of the atmosphere. For example, the atmospheric density was huge. So they were afraid that they were going to run out of room to slow down. Therefore, they used lift actually to gain altitude, to be able to make sure that they could slow down and do all the activities before touching down. So that's why they used lift, but it was unguided. Obviously, whenever you have a lift vector, now you need to control the direction of that lift vector. That forces you to have attitude control in the vehicle. So you have a set of thrusters, an INU, where it keeps your lift vector pointing up in the case of a Viking to gain altitude. Then came Mars Pathfinder and the Mars exploration rovers. Those were ballistic entry, so there was no center of mass offset, there was no lift vector. And one thing that you tend to do, just like a bullet, what you give it a spin for stability, you give it a spin at 2 RPM, in which case if you do have a little bit of lift vector because you left a CG offset, the error of that lift vector gets averaged out. So that's a good thing. That's why we like to give it a spin before we go in. And in these cases, both Pathfinder and NER, because there was no lift vector, is unguided, and we have higher difficulty achieving higher landing site altitude. So I'm going to skip Phoenix for a second and go directly to Curiosity. Curiosity, just like Viking, had a lift vector, okay, and it trimmed about 20 degrees, and that lift vector was used for the same reasons that Viking did, to gain altitude and have access to higher landing sites, but also, and this is the novelty, the first time he used that lift vector to guide the vehicle. Okay, and the way that works is when, in terms of going correcting cross-track errors, it's just like an airplane. You point, if you are off the left, you point the lift vector to the right, and you move you to the right. If you are off on the right side of the landing target, you point your lift vector to the left. That's exactly how you fly an airplane. For range, it's a little bit more complicated. If you try to come up with a prediction, if you feel that you're going to overshoot, then you remove lift in such case, which makes you fall into thicker areas of the atmosphere, increasing drag and slowing you down. And the same, the opposite, if you are going to fall short, you put more lift, it brings you stay higher in the atmosphere where it's less dense, and that reduces drag and makes your trajectory, it extends it, and corrects for that. So that was Curiosity. Now Phoenix started was going to do originally what Curiosity did for the first time. It was going to be lifted and it was going to be guided. Okay. Now, one of the first things that happened in the project when there were scope issues, they decided not to do guided entry, that they have already a full plate and full risks that they need to retire. So they removed the CG offset and they removed the capability to be guided. But they did leave the 3-axis stabilized control. So they didn't give it a spin, just to keep it as close as possible as the Viking heritage on which it was based. Later on in the project, they discovered that there was an issue that we also have to deal in Curiosity in Mars Science Laboratory of error, the interaction between the RCS jet firings during that 3-axis attitude control during entry and the supersonic flow. That is a very complex interaction that in some cases might actually change the direction or make it very ineffective the control of the RCS thruster. So it got to the point that the risk was high enough that they decided to increase the deadbands of their controller in such a way that only if the vehicle really, the attitude started to oscillate a lot, then the system will come in and stabilize it. So at the end, Phoenix ended up being ballistic like Mars Pathfinder and Spirit and Opportunity, but without a spin. Okay, and so that's the history of all that. I hope you were able to follow. So let me talk a little bit about the guidance algorithm that we used in Curiosity. It really was very closely based on the Apollo guidance that was used for bringing the astronauts back onto Earth. Apollo, again, was also a lifting body. And the way that works is the following. First of all, I mean, the whole purpose of the entry guidance, is to make sure that the vehicle is in the right place when you open the parachute. Okay, so that's the deal. So after you open the parachute, there's no guidance that you can do in this vehicle. So and you want to open the parachute as soon as possible. So we have a velocity trigger in Curiosity. So once we get to the right Mach number, as told by our inertial propagator, we open the parachute. And at that point, we want to be on the right place in the landing ellipse. There's some Kentucky windage there, so because we know that the system continues to decelerate, but in the right place. So then at the end, we touch down in the center of the ellipse. So that's the idea. the way that this Apollo guidance system has a range control and a cross-track control. The range control works by first of all, we need to have, both of this requires having inertial propagation. So right before we take the plunge into Mars, there is a navigation state that is computed here on the ground that gets uploaded to the spacecraft. It gives us a position and velocity of the vehicle at a certain epoch in time, okay, which was chosen to be 9 minutes before we hit entry interface. That's for translational. As far as attitude is concerned, the cruise ACS attitude system provides the inertial orientation of the vehicle and gets loaded into the IMU, and now the IMU propagates, it's a Honeywell MIMU, propagates 6-axis attitude translation based on that initial condition. And during this part of the flight, during entry, that's the only sensor that we use, okay? The radar will come out later on. From that, we can, given that inertial position, we can determine what's the range to the target. On board, we also have a reference trajectory as part of the Apollo algorithm that tells us, given a certain given velocity, what should be our range to the target. And then we have a range predictor function that, based on what is the drag and the vertical velocity that we're experiencing at that point and the reference trajectory, it predicts what's going to be the range to the target when we get to the right velocity to deploy the parachute. Then from that, we compare that range to go to parachute deploy relative to the actual range to go to the target, and from that you can compute an error, which would be a downtrack error. And for the downtrack error, then there's an algorithm that tells you how much you have to change left in order to compensate for that if you're overshooting or undershooting. And that's the lift command generator that I call. And then once you say this is the L over D that we want to get on the vehicle, then there's a bank command generator that says what is the bank angle that you have to have such that the projection of that lift vector on the vertical is the correct one. It's a very simple but extremely robust algorithm. So here it gives you a little bit more details. It shows you how the predicted range is a function of this reference range you have in the reference table, plus corrections that you make due to the fact that the drag that you're experiencing at this point, measured by the IMU, is not the one that you should be having according to the reference table, and the same with the vertical velocity. The correction to the L over D is also is essentially like a gradient approach. It shows you compute the range error to the target, and then you multiply it essentially by constant, and you add that to what you would like to have left in the reference trajectory, and that would be the commanded vertical L over D. And finally, very simple trigonometry. Now you find what's the right roll angle that would execute that lift up amount, L over D, vertical L over D. So that's basically, I don't have too much time to explain in more detail, and also Gavin Mendek of JSC is the real brain behind this. So if you have questions, you can also address them to him. So for lateral control, I mean, while we're doing range control, we're not paying too much attention to lateral because we have to use this roll control to actually put the right value of lift in the vertical direction. So what we do is actually we have a strategy where you keep lateral errors or heading errors under a certain bounds. So you can see the red and blue lines. And whenever you touch those bounds, you actually do a roll reversal and you point the lift vector in the opposite direction. And because those bounds are actually becoming narrower and narrower, by the end of the range control region, which ends at about 1100 meters per second, then you would like to be close to zero range lateral error. And now you enter another phase called heading alignment. That is actually does behave like the way one flies an airplane. You compute a cross-track error, and then you proportionally modify your lift, and you're flying lift up during that time. So then if there is no range control errors, no cross-track errors, the lift vector is pointing up. So that's very, very, very basically how the system works. And here's just to give an idea how the different ellipses corresponds to the different missions. You can see Viking has huge landing ellipses because they have huge first of all, they were not guided, and second, they had, because they were the first, for large unknowns in the atmosphere of Mars, even actually even the location of where Mars was also highly uncertain. So through the years, even before we introduced entry guidance, those ellipses were actually being reduced as we learn more about the atmosphere of Mars, and also we improve our navigation, ground navigation techniques, and also we learn better where the position of Mars is. So when we get there, we land in the right place. But in order to make that last big jump in capability that would allow us to visit a place like Gale Crater. You can see here Gale Crater is in the bottom. You can see that the only one that could have gone to this place is Curiosity, and that was due to the fact that it had entry guidance. So this is a perfect case where GNC came here to actually did a good job in improving the science return of a mission. It was fundamental. So I'm going to skip the parachute descent phase. There's not much that happened from a GNC point of view, except that that's where we actually the radar altimeter and velocimeter takes place and finds the position of the vehicle relative to the ground, which is very important, but we don't have enough time to talk about it. So let's talk about power descent. And I'm going to have to speed up a little bit because it's going very fast. So I'm going to show you this plot. They took the vertical axis, the y-axis is the vertical touchdown velocity, and the horizontal axis is the horizontal touchdown velocity. So and shows you all these architectures that I showed you originally. So starting with Viking, it was a soft lander, landed on legs, 2.4 meters per second vertical velocity and about 1.5 horizontal velocity. And it was a great success. And then 20 years later comes Mars Pathfinder. It was two things makes Pathfinder different than Viking. One was that it was a faster, better, and cheaper. And at that point, it was clear that as such, you could not make a mission of the complexity of Viking with all the GNC and radars and IMU. Okay, so, and that was one thing that influenced the design. So they needed something very, very cheap to land on Mars. The other one is that this legged lander thing, they actually had some problems in it. If you land on top of a rock or in a slope, you can actually tip over. So they, my mechanical friends, they were looking for ways of, solving both problems and get GNC people out of their place, because we are very expensive with our toys. So they proposed, well, let's just use an airbag and a parachute. Okay, so that's that. I'm going to use my arrow here. I hope it works. That's this blob here. In reality, that blob, it never happened. Beagle, I believe, tried to do that. In Mars Pathfinder in the 90s, they looked into that because that's the simplest system you could ever have. But the vertical velocity, the terminal descent velocity was just too high for what an airbag could do. An airbag can design an airbag that can go up to 12 meters per second or survive a vertical impact 12 meters per second. So that was a great attempt, but they actually had to do something. So that something was put in retro rockets, and that was really the Mars Pathfinder architecture that you can see here. It has a retro rockets. It has now a radar altimeter. So now bring the GNC guys, help us with this thing, and that's how I get involved in this world. So there's a little bit of GNC, and notice that with this architecture, yes, effectively now, because you can apply the brakes at the last second, you improve dramatically your vertical velocity, but actually the horizontal velocity, we made it worse, believe it or not. And the reason for that is because this system is so passive, there's so little GNC in it, is that when we fire the rockets, we are just counting on the pendulum properties of that descent system. So if you actually, to be vertical, and so if you actually get a wind gust during that time and the vehicle is at an angle relative to the vertical, when we fire the rockets, we get a cosine effect on the vertical channel, which is fine, but we get a sine effect of the angle and we get a big whack horizontal velocity. So with the Pathfinder approach, we fix the vertical velocity of the super passive system to make the horizontal velocity worse. So those airbags could actually rupture at those horizontal velocities. But in the case of Pathfinder, it was within the risk that we could tolerate at that point. We were landing at night where the winds were not higher. When we go back to Mars with an airbag landing later on with Spirit and Opportunity, that happened after the Mars Polar Lander failure, and the there was no tolerance for failure. So we wanted to use an airbag system because it was the last system that worked on Mars, and we knew how to do it. But we knew about this Achilles heel that was the sensitivity to horizontal winds. So we were asked to fix that, in which case we added more GNC. We put out not only one IMU, we ended up putting 2 IMUs in the system that would, and a camera to compute horizontal velocity. So it was an extremely complex system to reduce the vertical velocity from that value, the horizontal velocity to now a velocity that it was compatible with the airbags. And that worked. Spirit actually fired the system because it was actually hit at the last second when we fired the rocket. It was like the perfect poster child for this design, and it brought the velocities way down within the capability of the airbag. You know, with this system, that it was kind of the worst possible worlds in terms of an active system, complexity of GNC with all these sensors, and very complex to model and analyze. So through all that, Phoenix came back and essentially replicated the Viking architecture, but with more economical sensors and actuators, and that was a big success too. But all of this was a little bit of academic to some extent, but because when it came to landing almost a ton rover, none of this approach worked. Okay, thinking about a big airbag that could actually be bouncing with a 1-ton rover inside didn't pass the laugh test. That didn't stop us from thinking about it though. And but not for long. So that's how we. So then, in this circle that I just showed you in terms of touchdown velocity, we went full circle. Not only improving, so now we want to put enough GNC to bring velocities down, but actually we want to bring them down so much, even below Viking, such that we can land the rover on its wheels. Okay, so that's how the Sky Crane architecture is based. It's based on the fact that now GNC needs to do most of the lifting. In an airbag system, was the airbag doing most of the lifting. In a Sky Crane architecture, is GNC with its sensors and algorithms and actuators have to do all the lifting. So if you want to see how the motivation between the Sky Crane came, it's, this is just a motivation. This is not, there were multiple people involved in this, and exactly how the story happened it's like any idea. It's very difficult to trace. But the truth of the fact is that what we called at one point a rover on a rope, we already were doing that. Okay, it's because the airbag landers were, they had a rover here, and we had thrusters up there. So we were kind of doing that. Okay, so the only thing is that propulsion system was very rough. Okay, and just let the system drop. So we also knew how to control velocities very well if you put the right IMUs and the right thrusters, like in Viking. Okay, so why not replace this rough coarse system here that we have in the back shell on the airbag landing system by something that is vernier, with the right sensor, the right actuators, and to the point that now we can control the velocity of that vehicle and the rover that is hanging. To the point that not only we don't need airbags, but we can actually land the rover on its wheels, and that's what the Sky Crane is. But it's as simple as that. And one of the things that we discovered a whole bunch of new features of the Sky Crane after, in some ways, it was invented. Like, for example, we discovered that, hey, look, now we don't have to let in legged landers, you shut off the engines the moment that any of the pads touches down, because otherwise the vehicle, if you land on a rock or on a slope, the vehicle starts to tilt, and that will apply an horizontal thrust and the system tumble. So in all the legged landers, you need to terminate very fast, within milliseconds, all thrust the moment that any part of the vehicle touches down. And that increases loads and actually might make the system tip over. In the case of the Sky Crane, like any crane operator working on a port knows, you can actually continue lowering the payload until the payload is safely with all its wheels or all its surface on the surface of the Earth or on Mars, in this case. Okay, so we can actually, that's the beauty, because the thrusters are up there in the sky, what we call the descent stage, which is here where we have the thrusters and the IMUs. So that's one of the features. So also that allows us to land and be stable in very large slopes, and even another feature that we have, by virtue of the fact that we land on the mobility, on the wheels of the Curiosity, well, those wheels were designed to go over rocks. So we can actually land on pretty big rocks, and the system would contour to it. So essentially, we discovered that the wheels of the rover not only were great wheels to move from point A to point B, but they were great landing gear. So the whole system reinforced each other. And some of these features we actually discover after we have baselined it. So how to control this thing? Well, it ends up being that it's not as hard as a lot of people think. People, when they thought about this pendulum, they think about the inverted pendulum problem, but that's not what we're doing. We're doing the easy part. So essentially, I'd like to show this drawing here with the descent stage have a control system. In reality, is acting like a whole bunch of springs and dashpots. If you have a system like that, mechanically, you know that if you get a whack to that pendulum, the energy, the descent stage is going to move relative to ground in this case, and the energy is going to dissipate through the dashpots, and the system is going to be stable. So that's the control law that we wanted. So, but what does it really mean? Obviously, we cannot put a dashpot and a spring. There's no on Mars, so we need to do that with our thrusters and an IMU. What we're doing, that's equivalent of saying we want collocated control and sensing, and we're really what we're doing is we are phase stabilizing all those modes. Okay, that's once you do that, and as long as the frequency of all these oscillations or these modes are within the place where you have phase margin, you don't even care exactly. You are very robust to uncertainties of where those frequencies are. In order to do that, so that was the design principle. And early on, we decided that we wanted to be able to have a system that it was fairly stiff to be able to fight disturbances. So we asked for a very rigid structure, so then our sensors and our actuators, we can call them collocated. We didn't want to give up our sample delay. Okay, so early on, we told the avionics people and the software people we want 64 hertz sample rate. Originally, it was 8 hertz. They were not happy with that request. But Viking had at one point was 40 hertz. So I used that to shame them into giving me the 64 hertz because that's something that those are margins, that you want to get here on Earth. And there is one area that we have made tremendous progress was computers and software. So there was no way that they would not give me the 64 hertz to make this much more difficult problem easier to solve, and that's what we got. Then obviously you want to have high bandwidth IMUs and MLEs. The Mars MLEs we need are the Mars landing engines. Those are throttleable valves, throttleable engines derived from Viking. And to be honest, if that one had not the right bandwidth for us, we would have been in deep trouble because we had to use lower bandwidth, less disturbance rejection. But it ended up that we knew that it was actually very high frequency response, both the valve and the actual decomposition. So all the oscillation modes and also the actual modes were phase stabilized. And then the structural modes, the one above 16 hertz, they actually have a roll-off filter to gain stabilize. So it was as simple as this, and it behaved just as we expected, and it was not a very, obviously everything has to be done with care, but it was not the inverted pendulum unstable system that a lot of people thought we were solving. So the touchdown detection was another interesting part of the Sky Crane. One of the prevailing theories at one point was that Mars Polar Lander failed because the touchdown detection was prematurely activated due to noise in the system when the legs deployed that actually made the contact switch close. So one of the, we still were suffering from the big trauma of that touchdown detection. So people were very concerned about that the Sky Crane needed to have a touchdown detection. The airbag landers don't have that. So, but it turns out that it was a very, very, again, the Sky Crane had a feature to it, hidden, that we discovered that made our lives very easy. Essentially, you can actually make the system behave like a big scale. The system is going at constant velocity, 0.75 meters per second vertical velocity. That's what the control system is commanded to do. Before the rover is on the surface, thrusters has to be commanding enough force to actually sustain, to be able to support the weight of the whole system. Okay, times the gravity is essentially the mass of the full system times the gravity of Mars. Well, when the rover finally arrives and is being supported by the actual surface of Mars, half of that weight disappears because that's pretty much the same weight of the rover as the same stage. So if you just monitor the thrust that is being commanded to continue going at a constant velocity, that's very good indication that the rover is being supported by the surface of Mars, or that the cable was cut prematurely, but let's put that aside. So it was a very, very actually robust, and the signal to noise ratio was awesome. It was, it was an easy detection, and that was the way, and it worked fantastically on Mars. It just monitor the amount of commanded thrust that we need to send the engines or the control system, and when it goes down a certain threshold, then we know that the vehicle is no longer being supported by the engines. So a few more charts here, and so other nice things about this, the sky crane that we liked is that you can treat the sky crane essentially a lot. We used to talk about the launch vehicles. You can design the launch vehicle separately from the payload. Actually, you have a family of launch vehicles. So we were thinking about the descent stage the same way, that you can the payload, the thing that is hanging, could be designed separately, the same way that a payload that rides on the launch vehicle. So we like that, decouple, divide and conquer. In our case, it didn't come out exactly the same because we only have a single computer in the system for economical reasons. Now, from technical reasons, we actually would have liked to have our own computer. So we only have a single computer, so that's where the analogy with a launch vehicle ends. But in the future, it would have been a nice augmentation to have our own computer in the descent stage. And then the other thing that it was nice about this architecture is that again, the pendulum dynamics is really, and the control system is very easy to analyze. And we felt very comfortable doing that through simulations and body charts and all the things that the control system engineer has as its tools. And then the difficult part of the rover entering contact with the surface and the loads on the wheels and the stability, that's easy to test. So that's pretty much was the philosophy behind the VMV, the verification and validation of the sky crane. Now, in order to be able to design this system that was so, in order to land on the wheels, you really needed a high performance GNC system, not just the algorithms, but we're talking about the sensors and actuators that require a new development as far as the Doppler radar, 35 gigahertz pulse radar that was developed just for curiosity. It was a very expensive but we ended up with a very accurate sensor that was required to be able to reduce those velocities to the values needed to land on wheels. So and then we had to use we resurrected the Viking engines that were throttleable engines. It's the same cat bed and rocket design, but with a new valve. The actual throttleable valve was a modification. And again, that's also what we needed to be able to control the velocities. And that was also another development that was not cheap. And then obviously we had to develop a brake to lower the rover through the bridle slowly. And obviously a lot of analysis and testing of the structural model testing. So obviously when people say that the GNC, we can bring the cost up, it's true. We bring a lot of performance to the table, but we are not. Our toys are expensive. So, but in the case of Curiosity, it was within the capability. So I'm going to really speed up now. So as far as the another VMV, we thought about that we needed to come up with a end-to-end test of the sky crane. And but in reality, then after thinking and the cost and the intellectual tax that requires building this facility to do end-to-end testing, we nixed it, and instead of that, we've decided to pretty much do do a very good job characterizing each element. Like for example, the radar. The radar is a perfect example. Okay, we actually had 3 venues, including an F-18, to be able to test the radar on helicopters and to test the radar under all the conditions. So that was the deal that we made with the project. We won't have an end-to-end matter of all hot fire test, but we're going to characterize each one of the boxes extremely well, and then we're going to put a simulation, okay, a high-fidelity simulation, which we did with our friends in Langley using POST, and you know, so that was what we did, and at the end we have very, 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 very few surprises on Mars. It actually behaved like we modeled it. So so it worked, as you know. We landed safely. First use of the sky crane, first use of entry guidance. We landed 2 kilometers, 2.2 kilometers from the center of the ellipse. We are very happy with that result. We also, the knowledge of the position was actually very good too. I mean, even, you know, we were better than 500 meters position knowledge error, and this includes even the knowledge error from the ground navigation. So we're very happy at the performance of the system. We got what we invested on, and we got the advantages that GNC can provide were proven. Conclusions is, you know, we have had number one, a lot of opportunities on Mars to try different architectures, some very expensive like Curiosity, some cheaper like airbag landers, but with less robustness to landing, or even Phoenix. Phoenix eventually succeeded where Mars Polar Lander failed, and it is actually a lander closer to the cost and performance, to the cost of an airbag lander, not as robust to rocks and slopes, but as you can see now, there is another mission using the same architecture inside, so there's plenty of uses of that type of architecture. Another thing that we learned with Curiosity is that by bringing the multidisciplinary teams like together early on, like mechanical engineers and GNC engineers and system engineers, we can actually come up with these multi-discipline solutions like the sky crane. The sky crane could not have been invented only by mechanical engineers or only by GNC. You require this group of people, which, by the way, they have been working together and developing personal friendships all the way through Pathfinder, okay, in this community, and including people also outside JPL too, through the Mars Polar Lander and Phoenix experiences. So there was an intellectual journey that we had to take through all together, and if we could not have done it, or short-circuited the history to come up with this type of solution. As far as the future is concerned, we have plenty of room to do and exciting things we can do on Mars with more elaborate GNC. We can do pinpoint landing, hazard detection. We are developing the capability now, having sensors, camera-based sensors, to actually make a position fix, comparing an image with a map and determine the landing location. So you can use that to pinpoint land or to know where there is a close safety zone. So by doing that, you can go to places that are more dangerous and within the ellipse, because you have these safe places. So there are plenty of things to do. The concern and the challenge for our industry is that we need to keep the cost of our systems low in order to be able to make it to these missions. And that is the big challenge. That's the thing that worries me and keeps me awake at night, is the fact that sometimes that money is not there to develop these very expensive sensors, and we need, and without the project money, we cannot bring it. So it's kind of a chicken and the egg problem. So with that thought, I'm done, and I'm ready for some
questions. Yeah, we have a few minutes for questions. I really appreciate you trying to compress that whole story into 50 minutes, and personally, I appreciate you taking as much time as you did. I think it was on chart 13, you know, explaining the differences between the ballistic and lifted and guided trajectories. There was a lot. It looked like a simple chart, but there sure was a lot to that. So right off the bat, we've got a couple folks have asked very similar type of question. Walt England from Langley and Ken Lepsock from Goddard. They're both poking at this issue of, you know, how scalable is the sky crane architecture. And I guess we'd like you to comment, if you can here, a couple minutes here of what do you think the upper limits are of performance are for this MSL Skycrane architecture in terms of the amount of landed mass, the landing altitude on the surface of Mars, and the landing accuracy?
Well, as far as the landing altitude that's more dictated by other elements that happened before, right? Like the ballistic coefficient and parachute sizes and things like that. The Skycrane doesn't dictate that much. As far as the upper bound, I mean, definitely we can go several hundred. I mean, there's no limitation, and if there is a limitation, I would think is from a mechanical side, right? At what point having a bridle system that can tolerate, several tons of weight, so that would be more of a mechanical issue. From a GNC point of view, I believe if we have the right thrusters to do it, we can do it. I would wonder. So from that point of view, I believe that there's from a GNC point of view, I don't think there is an upper bound. I would ask, mechanical engineers at what point, the whole lowering this thing with a brake, and if you're talking about 10 tons, can you actually do that? So the answer, mechanically, I don't know. GNC, if you give us the right thrusters, we have the right sensor, doesn't change. We can land it.
Okay, thanks. Appreciate that. I guess I wanted to ask you something about in terms of the challenges you faced. You had that chart where you showed the sensors and actuators, radars and thrusters and IMUs. Of course, we need those to architect GNC system for this application, any application. But I would have thought one of the really pressing challenges you guys faced was this whole business of the interactions of the jet plumes, right, at the high velocities you were experiencing, right? And I think some of us at NESC have looked into that in the aerosciences area and the flight mechanics area. Do you see that as well, let me ask you this. Do you think we need, it's a bit of a leading question, but answer as you see fit. Do you think we need more data from wind tunnel tests? Do we need better tools? Do we need better methodologies to handle those problems in the future, the whole business of the plume jet interaction? Any comments on that?
Yeah, I mean, it's a little bit outside my field of expertise, but it seems to me, yes. I mean, at the end, our models, we added a lot of conservativeness in our models. We put, whenever we fire a thruster, we have errors we put errors in the system of the direction up to 30 degrees. So we were able to kill it with brute force, and we actually did move the thrusters, and the fluid dynamics tools that were used were good enough to guide us what would be a better place than the other. But at the end, the amount of uncertainty that we have, it was very, very large. And thank God, in our case, we have enough control authority that we didn't make us do anything silly. Sometimes if you are too conservative, you actually end up making the system less robust. In our case, we were able to show that with that conservativeness, we will still have a mission. Now, it might be the case that in the future other missions don't have that. So, again, I'm not an expert, but I think one of the things that we were all surprised that we were having this problem. We started asking, well, Apollo had this problem, so how did they solve it? And people looked into the literature, and there was not much information on that. So we don't know whether it's because they just try it and it worked, which is something that you can do with maybe with an Earth-based EDL system, but with Mars, it's too far to do that type of experiment or do even here on Earth. So it's, well, for Apollo, that might be the right thing to do for them because they have a pretty large budget back in those days. For us, we couldn't do that. So for me, that was very frustrating. So that's everything that is, and the same with the parachutes. It's the same thing, right? Still there's a lot of art in those things still. That it would be nice if we can remove the art and bring more science to it.
Excellent, thanks. Let's see, we got a couple. I think we have time for a couple more questions here. This has really generated quite a few, and I'm trying to combine a couple of questions here. Mike Aguilar asked you, could you maybe provide a little more detail on the processing capability of the GNC computer, onboard computer, flight processor, if you will, on Viking. I mean, on the growth we've had in the capabilities. In particular, how were we able to pull off that Viking lander back in the mid 70s with the kind of flight processors we had? And we also have a somewhat related question from Anthony Intravea, who asked about given the Apollo and MSL entry, descent and landing design parameters, could you talk a little bit about the analog versus digital implementations and the kind of loop responses versus performance that you had? So I think it's kind of a general question about the a little bit of digital versus analog, and comment on the capabilities with Viking versus what we have these days. I was intrigued that you said you had to shame the avionics folks into giving you the sampling rate you wanted by telling them what they had on Viking in the 70s, right? That was I found that amusing.
Yeah, well, yeah, and obviously, our computer, we have a PowerPC. I think it's 100 megahertz. It's, I don't know, flops. I don't remember that stuff. It was very powerful to the point that we actually, for the data editing of the nav filter, for the navigation filter, what we take in radar measurements, we actually, because we were afraid of not having enough juice and it's very data processing intensive, we actually had a background task, doing that job, and we gave it a full 1 second to finish that job, and the thing was done within 20, 30 milliseconds. So we didn't know that in the beginning. So we get to the point now that our computers really, they are not slowing us down. Now, when you compare, and this is a statement I had made at JPL, and I love to make it right here to this community. When you compare what we're doing today with what Viking did with a computer that is probably less than computational power than a watch these days, the truth of the matter is that we are not solving a problem that different. Okay, the Sky Crane doesn't require that many more lines of code what Viking did. So I ask my avionics people and software people, why is it that our lines of codes has gone out by orders of magnitude? And one of the, asking about what are the things that made us pull our hair, we were equally concerned, or maybe more, about the whole system having a reset of the computer, just like our computers sometimes reset, than we were about getting the physics of EDL wrong. So we are, in my opinion, and I'm not an expert, I'm a sufferer of avionics and software, I call myself. The fact that we have all this computer power and we can do all this complex electronics doesn't mean that we should. And we actually should strive to more simplicity, so then we have systems that are more reliable. I mean, we were really, really concerned that the system was going to reset during EDL. And that was almost a bigger concern than busting a parachute or that the Sky Crane would not going to work. So we need to start developing, in my opinion, avionics and software for GNC, by GNC, of GNC, right? I mean, because these multi-purpose systems that are used for both, for GNC and EDL, for mission critical, and for science, it compromises the possibilities of success. The second one about analog versus digital, well, everything was digital, right? I mean, obviously, I mean, the little dashboards, and that's an analog system, but I mean, essentially by making it go high sampling rates, you approach the analog situation. And our bandwidth the additive bandwidth for during the Sky Crane, additive control bandwidth was in the 1 hertz range. What we call the axial mode was also 1 hertz. Obviously, the translational horizontal motion, that was an order of magnitude less because you needed frequency separation. So those were actually pretty high bandwidth for our type of spacecraft, but we wanted high disturbance rejection, and also we wanted fast response because we were blowing fuel 4 kilograms per second. So whenever we throttle down, we wanted that, we always have to put some time for the system to settle before we actually separate them. But we don't have to wait 10 seconds for the system to settle because that would have been 40 kilograms of fuel. So we wanted fast response, high disturbance rejection, but that's why we were implementing 1 hertz bandwidth controllers.
Great. Thanks for those insights. Why don't we try one last question here? I think it'll be fairly short. We do have some other questions that have come in, and I'll be passing those on to you, and you can try to follow up with those, Miguel, if you will. So this question came from Robert Denise, I believe out at JPL, and says, you addressed all landers but MPL. I think you alluded to Mars Polar Lander. The question was it a lifting body or merely ballistic? I think you talked about it being a legged lander, but maybe you could say just a quick couple words about MPL. I thought it was very much like Phoenix, but go ahead.
It was, I believe, if I remember correctly, definitely a legged lander. It was like Phoenix. Phoenix is like the reflight of that architecture. But I believe they did not have a lift from the beginning. It was not part of that from the beginning. But it was three-axis stabilized during entry. It was not spin stabilized. That's what I remember. But I mean, definitely no guidance, because I remember that those two missions were approved at the same time, Mars Polar Lander, and it was not called Phoenix. It was going to call Mars 2001. And Mars 2001 was going to be the first use of entry guidance. Okay, so so I know from that Mars Polar Lander, there was no entry guidance, whether it had a lift vector and flew lift up, maybe, but I don't remember.
Well, it was several years ago. We'll give you that one. Okay. Well, look, thanks for being so open and frank with your answers there. We do have more questions. We couldn't get to them all in the time we have here. In fact, we spilled over a little bit into the next hour, but I think this is such an intriguing topic. That's fine. So what we'll do, Miguel, we'll gather up the questions. I'll make sure you get them, and we have email addresses. If you wouldn't mind taking a few minutes after this to follow up with those individuals that didn't get their questions posed here right now as part of this real-time webcast, I'd very much appreciate it. Okay. Let's see. So I did want to take this opportunity, just a quick commercial break. No. There is this newly formed entry, descent, and landing community practice, NASA community practice. It's on the NASA Engineering Network, or the NEN. It's meant to address this whole, as you've heard Miguel talk about, this whole multidisciplinary area called EDL. A lot more than just GNC. That's been the focus of today's talk, but obviously it's really quite a system engineering accomplishment that these missions have been successful, I think. So like the other, this is one of many communities of practice we've got online at the NEN. It was stood up to help facilitate communications, technical communications between the centers and the institutions and the people working at those places that have an interest in this. So I think long-term the intention is for this community to be able to coalesce thoughts and positions and ideas and be able to provide inputs and recommendations on some of the key technical issues that relate to the current and future EDL technology investments and technology requirements. So if you have an interest in this area, I'd urge you to go check this new community out. Join up if you think it's a good fit with your individual engineering interests. Like all the communities of practice, you can go to the nen.nasa.gov website and click on, you see it up there at the top of the chart, it's communities. And you'll find all the communities, including this new EDL community practice. So I am looking forward to the next year and trying to line up another continuing series of these GNC webcasts. If you have ideas where it would be useful, you think it would be useful to have a focused topic, a GNC focused topic for a webcast, or even better, if you consider yourself a subject matter expert in a particular area and you want to volunteer to give a webcast, please contact me directly. So at this point, I'd like to say thanks, Miguel, for taking the time to pull this presentation together, and
thank you. It's a pleasure.
Drop in the GNC specific parts of it. Well, it's really been very insightful. And I'd like to thank the audience for participating with us today, and we look forward to you being with us in July when we have Tim Crane talking to us at the next webcast event. So thank you and goodbye.